everyone. We're going to get started. This is the second to last year lunch, and I'm very happy to introduce Alex Wang. He's a PhD student here at CMU, and today he's going to talk to us about this very hard to pronounce thing, bounds from Laplacian Eigenvalues.
All right. Thank you for the introduction. So today I want to tell you about some recent work. The title of this talk is Hardy-Muckenhoupt Bounds for Laplacian Eigenvalues. Before we get started, I just want to say that there are a lot of kind of daunting names up here. I want to say that a lot of this stuff is a lot simpler than it would seem at first. So just keep an open mind. All right. This is.
How to pronounce the second name?
I think it's Muckenhout. I'm not sure. Yeah.
It's a lot simpler than it seems, but why don't you just make it simpler then? The simplest version
yeah,
of it, so we understand
that's what I plan to do today.
Change the pleasant's name.
Yeah. Yeah. So this is based off of joint work with Gary Miller in the CS department and Noel Walkington in our math department. All right. So I'm going to just set up some of the quantities that we'll be studying today. So I'll be talking about weighted connected graphs. For me, that's a 4-tuple V, E, mu, kappa, where V and E form a connected graph in the usual sense. Mu is going to be a function from the vertices to the positive reals. I'll call those the masses of the corresponding vertices. And I have a vector kappa from sending the edges to the positive reals, and I'll call those the spring constants. All right, so pictorially, that's this graph here. It's a connected graph. The vertices have different sizes, and so for example, for this vertex there, its size is mu of V, and the edges have different thicknesses, and the edge here, for example, has thickness kappa E. Right, that's its spring constant. The degrees, so for example, if this is my vertex V, the degree of V is just going to be the sum of the spring constants of the edges adjacent to that vertex. All right. So formally, the Laplacian is the matrix D minus A, where D is the diagonal degree matrix, and A is the weighted adjacency matrix. All right. So maybe there isn't a whole lot of intuition about what this quantity is, but I think it's good to try to understand how it acts as a linear map and as a quadratic form. All right. So as a linear map, L is going to take some vertex in RV, and it's going to produce for you a new vector, Lx, whose vth coordinate is, by linearity, dx of v minus ax is vth entry. And just expanding this definition, we'll get this quantity here. Right, so it's just a sum over all of its neighbors, the neighbors u of v, the spring constant between u and v, and the displacement xv minus x of u. Okay. For now, I just want you to notice that it kind of compares x's vth entry with the x entries of its neighbors, right? So for example, if x assigns v a value that's larger than all its neighbors, then this quantity is going to be non-negative. These are all positive values, and this is the sum is going to be a non-negative quantity. Right? Similarly, if x assigns v something smaller than all of its neighbors, then this is going to be a negative quantity. Okay. How does it act as a quadratic form? Well, you could just take x and take its inner product with Lx, and after some algebra, you'll see that it's going to be this equation, this expression here. So that just says that you're going to sum over all of your edges in your graph, the spring constant times the squared difference of the x across that edge. Okay. So I'm going to talk a little bit some more about spring mass systems and try to give you some intuition about why spring mass systems relate to the Laplacian. All right. So one thing you could imagine doing is you have your graph G, and we're going to try to embed it onto the real line. Right. So I'm going to embed it onto the real line going left to right here, and I'm going to embed it as sending the vertex V to x of V, some point on the real line. All right. And if you have your vertex V here, you could imagine asking what's the force acting on V. All right. Well, if we apply Hooke's law, right, then the force acting on V, it's going to have two components, right? It's going to be U is going to pull V to the right, and this vertex here is going to pull V to the left. Right, and the force acting on it is just going to be kappa uv times xu minus xv, summed over all the edges connected to V. Right? And we'll notice that this is nothing except up to the sign here. The Laplacian of x is vth entry. Okay? And one natural thing to do with a spring mass system is ask for its standing wave is to solve the standing wave equation. Right, so the standing wave equation is this line here. It says that the negative acceleration of v, that you have some fixed lambda such that for all v, the acceleration of v is equal to lambda times x of v, right? The position of x, the position of v. And if we believe that this is the force acting on v, and that force is equal to mass times acceleration, then you can rearrange this, plug it in, rearrange, and you get that you're looking for solutions Lx equals lambda mx. Okay? So if you forget about the rest of the slide, if you don't believe anything on this slide, that's fine. This is what I'm going to be studying. Right? I'm going to be studying solutions to this eigenvalue equation. And I just want to note that in this interpretation, the square root of lambda is proportional to the frequency. This proportionality, I don't really care too much. I just want you to remember that as lambda increases, the frequency increases. Right? So small lambda is small frequency. Okay? So I'll be studying Lx equals lambda mx, and I'll be talking about that in this talk. So it's an eigenvalue equation, so it's going to have v many eigenvalues. Right? L was a positive semi-definite matrix, so all of its eigenvalues are going to be non-negative. We'll note that 1 is an eigenvector with eigenvalue 0. Right? So what does this correspond to? You could think of taking your entire string mass system and embedding it at the value 1 on your real line. Right? So Lx is telling you the force acting on each vertex, and that's just going to be 0. Right? So you can take, so when x is the all ones vector, you can take lambda to be 0. Right? So that's one of the solutions. The Neumann problem, this is the definition of the Neumann problem, is to find lambda 2. Okay? Usually in spectral graph theory, people just call this the second eigenvalue. And I'm going to call it the Neumann problem to emphasize the implicit boundary conditions that we're assuming. If you don't know what those are, I'll explain them shortly. But for now, I'm just going to define lambda 2 to be the Neumann eigenvalue. Right? That's just the name I'm giving it. So by Courant-Fisher, Courant-Fisher tells us that lambda 2 is going to be the minimum over x of this quantity such that x is m orthogonal to your first eigenvector. Right? In this case, we know that the first eigenvector is 1, so we can just plug that in here. Right? So from now on, this is what we're going to think of lambda 2 as being. Right? So lambda 2 is the minimum over x of this quantity. This quantity is called the Rayleigh quotient, subject to this condition here. Right? And I'm going to think of this as the boundary condition. Right? Later on, we'll take this equation here, and we'll replace it with other constraints. Okay? And we'll do that to get a different version of a eigenvalue problem. Okay, so let's just look at this Rayleigh quotient here. So it's x transpose Lx over x transpose Mx. And by our previous calculations, we know that this quadratic form is just the sum over the edges, the spring constant, the squared displacement across that edge. In the denominator, we have the weighted L2 norm of x. All right, so it's just sum over all the vertices, the mass of the vertex, times the position of the vertex squared. Okay, so I want to convince you that lambda 2 is important and that people care about lambda 2. So in the computer science literature, lambda 2 comes up in a lot of places. So for example, it governs the mixing time of random walks. It's used to analyze Markov chains. The convergence of Laplacian solvers, often you also get a lambda 2 term. And some of these techniques are also used to algorithmically for things such as image segmentation or clustering. In other areas, such as in quantum mechanics, it shows up because it's related to the uncertainty principle, and in numerical analysis, it shows up because it shows up when we try to model heat flow. Okay? So you might try to estimate lambda 2, and that's what we're going to show you how to do today. But before I do that, I'm going to tell you a little bit about Cheeger's inequality and use that as a reference for the things that we prove. Right? So Cheeger's inequality. Cheeger's inequality has to do with the sparsest cut of a graph. Right? The sparsest cut of a graph, which I denote as cut, is just the minimum over proper non-empty sets of vertices, right, of this quantity here. In the numerator, you have the sum over all the edges crossing your cut. Right? So you have a partition. So in this example here, A is the first 3 vertices, and A complement is the 4 vertices on the right. So in the numerator, I have the sum of the spring constants of all the edges crossing the cut. Right, so for here, that's just going to be this one thick edge here. And we're going to divide by the minimum of the masses on either side. Right, so I'm going to sum up these masses, call that the mass of A. Sum of these 4 masses on the right, call that the mass of A complement. And I'm going to take the minimum of those 2. Right, so what do optimizers of this problem look like? Well, we want the numerator to be small, and in some sense that's asking us for that A and its complement are sparsely connected. We would like the denominator to be large, which in a sense tells us that we want A and its complement to both have a lot of mass. Okay? So after you've defined this quantity, Cheeger's inequality tells you that in the special case where mu is exactly equal to the degree, right? In the literature, this is called the case of the normalized Laplacian. Then you have that the sparsest cut is bounded below by lambda 2 over 2 and above by square root 2 lambda 2. Equivalently, I'm going to rewrite it in this way here. Right, so we care about lambda 2, and we're thinking of Cheeger's inequality as a way to use the sparsest cut to bound lambda 2. Right, so this is the inequality I care about. It's known, however, that both sides are tight up to constants. Right? And so this is not great for us because when lambda 2 goes to 0 and the sparsest cut goes to 0, when they're both really small, this inequality here is not tight, right? You lose a square. Okay, so keep that in mind. And now I'm going to tell you the main things that we're going to try to prove today. Right? So in our work, we define this.
Why do you think of sparsest class approximation to the lambda 2, even though, if I'm not wrong, lambda 2 is easier to compute than the sparsest cut?
Lambda 2 is easier to compute numerically, but I think analytically it's hard to get a clear sense of the exact value of lambda 2.
So Neumann's talk did that. He showed that his graphs had no small cut, so therefore lambda 2 is big. It's not unusual to turn it on its head. Alan Freed did that on his work on fixing time for computed volumes.
Okay. I have a question.
Yep.
Can you go back to the previous one there?
Yep. This way.
Why is s cut squared always smaller than 2s cut?
So this. So obviously, if you could scale the sparsest cut, then there would be no way where this could be true, right? I mean, this isn't a homogeneous inequality. But we are in the case where mu of v is equal to the degree of v, right? So that prevents you from scaling. I guess that's the. Yeah. I guess that's the reason why the obvious thing. So the obvious way to try to break this inequality is to scale everything, and this prevents you from scaling.
Is it obvious why that's true? Why s cut squared over 2 is less than 2s cut?
I can't give you an answer off the top of my head.
Simple Cauchy Schwarz or something.
Yeah.
To quote the hard direction.
What?
It's quote the hard direction.
No, I think he's just asking why is the sparsest cut at
Right.
most 4. That should be just some trivial inequality.
Right.
Uh-huh.
Okay. Okay. Right. Okay. So to compare, so we're going to define some value of a graph that we call psi2, and this is going to, in some sense, be a fuzzy version of the sparsest cut. Right. So psi2, I'm going to define I'll define it formally later, but for now, just think of it as being the minimum over disjoint non-empty sets A and B of your vertices of this quantity here, of this ratio. In the numerator, I have the effective spring constant between A and B, which I haven't defined. And in the denominator, I have the minimum of the 2 masses. All right, I'll explain the effective spring constant in a little more detail later. But for now, I want to tell you that when B is taken to be the complement of A, right, the effective spring constant between A and its complement is nothing other than just the sum of all the edges crossing that cut of the spring constants, right? So if we, for example, throw in an extra constraint here, which says that B must be equal to A complement, then we can replace this expression in the numerator with this term here, and we'll note that this is nothing, then in that case, this would be nothing other than the sparsest cut. Right, so we can think of this as a relaxation of the sparsest cut, where sparsest cut must partition, we are allowed to leave out some of the vertices. Okay, and we show that under this definition, once we're allowed to throw away some vertices, we get a much stronger theorem. Right, so if you have a weighted connected graph, this is an arbitrary weight. Right, mu does not have to be equal to the degree of the vertices. In this setting, right, so in the general setting, you have that lambda is bounded below by psi 2, is bounded above over 4, and is bounded above by psi 2. Right, so this gives you a tighter estimate for lambda 2. And it can also be shown that this 4 is optimal, right? So you can't replace this 4 with a different constant, a smaller constant, and hope that this to still be true. And you can't decrease, I guess, the constant 1 here. Okay?
And well, that's true for that psi?
Yep.
That symbol is defined for a cut AB?
It's defined as a minimum over the cuts. So let's go back. So
Minimum over those?
Yes.
Okay.
yeah. So in this example here, right, if I take these 3 vertices to be A, and these 2 vertices to be B, then mu of A is defined as just the sum of those 2 masses. Mu of B is defined to be the sum of these 2 masses. And the effective spring constant, you can think, right, if you, so I guess in this simple example of a path graph, then if you can imagine that if you had these physical springs, you could just tie them end to end, and you'll get a new spring with some spring constant. And that's what this kappa effective between A and B is. Questions? I think I missed first.
So in your new notation, what is psi 1? How do you define psi 1?
Okay, so I call this psi 2 because it bounds lambda 2. Later I'll talk about, remember how I told you that I would later replace the boundary conditions? When I replace the boundary conditions, I'm not going to answer your question now. We'll get to it later because I think it would confuse the audience if I tried to answer it now. I think I saw Nick next.
Yeah, it's a minor question, but the reason you put the approximate equalities, that's just because you haven't defined kappa effective yet, or are you still
No.
going to us even more there?
No, so psi 2 is going to be, right, so instead of having this min mass term, I'm going to have, what it really is going to be mu A inverse plus mu B inverse all inversed. So it's going to, right, it's equal to min of mu A and mu B up to like a 1/2. Yeah, the kappa effective, I won't define for general graphs in this talk, but I will tell you what it is for a path graph in a little bit.
That's how spring constants add
It,
in parallel.
yeah, it's exactly.
It's in parallel.
Oh, sorry. It's going to be like in series. How spring constants
In
add in
series.
series.
That's what
Or
they add.
sorry, in
I see,
series.
in parallel, it would just add the 2 or something.
Right.
But in series, it would go through the inverse formula.
Exactly.
Okay.
Yeah. So that's going to be the definition, or that's not the definition, but you can show that that's exactly how it ends up behaving for the path graph. Okay. I think.
That was
No.
also my question.
Okay. Sounds good. Okay. So this is the main theorem of our work. But today I'll try to sketch this theorem in the case of a path graph. Okay? All right. So we're going to take a little detour and talk about a different eigenvalue problem where I'm going to replace the boundary condition.
This is for mu equal E or?
No, this is for general, yeah, in the general case. Yep. And so while we're talking about this Dirchlet problem, I'll tell you guys about this very cool, very neat inequality that we found called Muckenhout inequality. Right? And in a sense, Muckenhout inequality is nothing other than a statement about the Dirichlet problem. Okay? All right, so the Dirichlet problem. Again, I'm only going to cover the path graph in this talk. So I'm going to think of my vertices as being labeled V0 through Vn. Right, so here that's V0, V1 through Vn. My edges are just the edges of the path graph. My masses are positive. And the spring constant, I'm just going to label by the right endpoint. Right? So this is kappa 1, there's kappa 2, up until kappa n. So the motivation for the Dirichlet problem is to try to solve the standing wave equation, where I'm going to fix this zeroth vertex to the position 0. Right? I'm going to stick my hand out, and I'm going to hold it at the value 0. Right? So this is just some intuition. Formally, after you do the same exercise I showed you guys previously, you're going to find that this is how we define the Dirichlet eigenvalue. Right? So it's going to look familiar. You're minimizing over x, the Rayleigh quotient, but instead of having x being m orthogonal to the all ones vector, we're now going to require that x0, the value at the boundary, to be equal to 0. Okay? So you can think of this as an eigenvalue problem. Yeah, I'm not going to say anything more about that. I'm just going to think of lambda as being defined this way, right? Formally, it corresponds to an eigenvalue problem of some submatrix of L's and M's. I'm going to just open this up so we know what it looks like, especially for the case of a path graph. Right, for the case of the path graph, it's just going to be the sum over all the edges from 1 to n, kappa I, the displacement across that edge squared. And then the denominator, I'm just going to have the sum from I equals 1 to n, mu I xi squared. And the constraint is, again, still just x0 is equal to 0. Question?
Yeah, sorry. So should I be physically thinking of lambda as corresponding to something in this? Like,
yeah. So, okay, so, right, so you could imagine that, like, you want to find a displacement of the vertices such that if they're standing at rest, if they start at rest and you let them go, they're going to oscillate around 0, where 0 I'm just going to hold there, but the rest is going to like act as a spring mass system and oscillate around that fixed point 0. And lambda is going to be like the square root of the frequency, or it's going to be the frequency squared.
when you say oscillate, it's like back and forth across
Yeah.
0.
Yeah. Okay. If the intuition doesn't make a whole lot of sense, this is just the formal definition of what I'm talking about. All right. So the optimizer is highly non-obvious, right? It's not obvious what to pick x to be to optimize this objective function here. But it is maybe a good idea to try to think about what this is in the case of n equals 1. Right? Question?
Many frequencies on which the
Right. So
is this the minimum one?
I'm looking for the minimum one. Yeah. So let's think about what this quantity is when n equals 1. Right? There's a single boundary vertex v0, and I have a single vertex not tied to the boundary v1. Right? Well, in that case, lambda is going to be the minimum over two values. Right? These are just going to be scalar values of kappa 1, the displacement squared, over mu0 x0 squared plus mu1 x1 squared. But I'll notice that I have this boundary condition, right? So I'm just going to plug that in straight away. And then I'm going to notice that the x1's squares cancel out. Right? So in the case of a two-node system where one is tied to the boundary, right, we know exactly what lambda is going to be. Right? We know exactly what the oscillations, the frequency squared is going to be. It's going to be kappa 1 over mu1. Okay? And so maybe we don't know how to deal with when n is greater than 1. But I'm just going to tell you, you have this graph here, n is greater than 1. I'm going to ask you to squint really hard until all the vertices here look like one single vertex, and all the edges here look like a single edge. All right? So formally, I'm going to pick some k and n. I'm going to let a sub k be the vertices after the kth vertex. So here, that's a sub k is these three vertices. And I'm going to create a graph for u, g sub k. G sub k is going to have two vertices, u0 and u a sub k, and I'm going to define masses and spring constants. Right, the mass on this vertex is just going to be the sum of these three masses, and the And the spring constant that I'm going to attach between these two vertices is going to be the effective spring constant between this vertex and that vertex in the original graph. Okay? For a path graph, I'm going to define my effective spring constant to be the sum of the inverse of the spring constant inverse. Right, this is just the usual spring constant, like how you add springs in series. But I just want to point out that as you add more springs, you're going to get a weaker spring constant. Okay? Right? Okay. And so we know for this new graph what its lambda value is. Right? Its lambda value is just going to be this spring constant divided by this mass. Okay? And I'm going to tell you, surprisingly, that this actually, that when you optimize over k, right, that there is some k you can pick for which the oscillation of this two-node system is going to be very similar to the oscillation of the original system. Right? So what do I mean by that? So I'm going to consider minimizing over k this quantity. Right? So let's see what happens when we push k to the end. Right? As k gets larger, your mass is going to get smaller, but your spring constant is also going to get smaller. Right? The effective spring constant. As you go to the left, the effective spring constant is going to get larger, and the mass is also going to get larger. Right? So there's going to be some optimal trade-off that you're going to pick, and you're going to pick that optimal k. And I'll define that to be my Dirichlet content. Right? Psi is just going to be the minimum over k of the oscillation of the two-node system defined by that k. Right? So just unwrapping this, it's just the minimum over k, the effective spring constant between v0 and vk, divided by the mass of the vertices after k. Okay? All right, so we're going to take a short detour now, and we're going to talk about Muckenhout's inequality. And we'll see that this is actually magically related to all of these definitions, and can be thought of as actually the reason why we defined things this way.
This is only for the path.
The path, yes. You can do similar things for arbitrary graphs, but I won't talk about that today. I'll state the theorem later, but I won't talk about it today. Okay. So this is Muckenhout's inequality. I stated it as a corollary because his full theorem is a little stronger. What I've stated here is just a subcase of his full theorem. So it says you have two positive functions on 1 through n, and you're going to pick c to be the smallest constant, such that for all y in Rn, you can bound this quantity by this c times this quantity on the right. Right, let's take a look at the quantity on the left first. It looks like the mu-weighted L2 norm of some thing in this thing in the parentheses. The thing in the parentheses is just a running sum. All right, so you could imagine that you had a y, and you're going to create a vector z as the running sum of the y. And this is going to tell you how to bound the the mu-weighted L2 norm of z compared to the kappa-weighted L2 norm of y. Okay, and he defines this quantity b, which is this thing here. Don't stare too closely at it for now, but it tells you. He tells you that you can use b to estimate c, right? As b is less than c is less than 4b, right? And this 4 is the same 4 that we'll get in a little while. Okay, so maybe at first it isn't clear how this relates, but I'm going to tell you. We could suppose we have some x, right? This is your position vector where x0 is equal to 0. I'm going to define for you yi to be the differences, right? In which case, this sum here telescopes, and you're just going to get x sub I. And this term on the right is going to be your squared differences, right? So now it should begin to look a little more familiar, right? We're going to, after doing that, we're going to take this to the right and c to the left, right? And we'll get that c is the smallest constant, such that for all x, with x0 equals 0, we have that this term is bounded below by 1 over c. Right? So we'll note that this is nothing except, right, if you minimize over x such that this condition holds, this is nothing but the definition of lambda, right, the Dirichlet eigenvalue. So I'm going to go ahead and minimize over x, and I'm just going to invert the definition of b. Right? So if 1 over c is the minimum, right, 1 over c is really nothing but lambda, and 1 over b is the minimum over this quantity. Well, this quantity, right, this is the effective spring constant between v0 and vk, and this is the mass on the right of k. Right, so that was nothing but my definition of psi. Okay, so this, right, so I'm just going to rewrite it in the language that we developed in the first part of the talk. If you have a weighted connected path graph, and lambda is the Dirichlet eigenvalue, and psi is the Dirichlet content, then we can estimate lambda this way. Okay. All right, so we're halfway through the talk now, and I'm just going to show you how to take this inequality and upgrade it to a Neumann, a bound on the Neumann eigenvalue, right? So the usual lambda 2 that people in spectral graph theory usually care about. But before that, I'm just going to tell you a few quick words about how you would attempt to prove the Muckenhout's weighted Hardy inequality. And I thought that there were a couple of very cute tricks there. So I wanted to just show you a very, very high-level overview of how you would do it. All right, so this is just a very sketchy proof sketch. So we're going to start with this quantity here, where this is the mu-weighted L2 norm of x, and or squared. And the goal is to bound it by 4 over psi, the kappa-weighted L2 norm of the differences. Okay? So the first thing you might want to do is you note that this is x sub I, and really we want like the differences. Right? So I'm just going to write it as a telescoping sum. Telescoping sum all squared. Right? And I want to upgrade this L1 norm to an L2 norm. Right, this is just sum over the differences. I want to upgrade it to like a sum over the squareds. So the natural thing to do is to apply Cauchy-Schwarz. Right, so if I apply Cauchy-Schwarz, I'm going to get this term here. But right, this isn't great because really we wanted like a kappa I in front of here. Or a kappa j, sorry. We want a kappa j in front of here. So okay, I'm going to start over. I'm going to, before I do Cauchy-Schwarz, I'm going to multiply by square root kappa j over kappa j. Right, and I'm going to group this as the first term in Cauchy-Schwarz and the second term, so that when I apply Cauchy-Schwarz, I get that term there for free. All right? It turns out that this is still not great, right? Because we want this inequality to be tight, right? I told you already that there are choices of mu for which this is going to be tight, where this is going to, we want this to hold it with equality, right? So if we want this to all hold with equality, then this term better be proportional to that term, right? And unfortunately, that's not going to hold for the true eigenvector. All right, so we're going to start again. And I'm going to multiply by alpha j kappa j over alpha j kappa j, all right? And I'm going to apply Cauchy-Schwarz, but now I have this extra variable of freedom, right? And I can pick alpha j, right? So, and like by what I said previously, I want this to be tight when I have access to, when x is the true eigenvector. Okay? So we don't know what the true eigenvector is, so we can't really pick alpha j. But we do have an estimate, or we do have, or Muckenhout had an idea of what the true eigenvector should look like. It turns out that we're going to pick alpha j so that this Cauchy-Schwarz term, this application of Cauchy-Schwarz is tight when x is the square root of this term. What is this term? So if you think about, like, you had your spring mass system, right, then this is 1 over the spring constant up to some point, right? So right, it's just 1 over the spring constant up to your k, and I'm just going to take the square root of it, right? And that turns out to be something that's very close to your true eigenvector. And it's so close that you can actually, you can finish the proof now. All right. Okay, so that's all I'm going to say about Muckenhout inequality. Okay, so, all right, so for the remainder of the talk, I'm going to tell you how to take the Dirchlet, the bounds on the Dirchlet eigenvalue that we got, and how to upgrade them to bounds on the Neumann eigenvalue. Okay. All right. So just to recap, the Neumann problem is to find the minimum of this Rayleigh quotient subject to these boundary conditions. All right. For the path graph, I'm just going to write it I'm going to write out what this is exactly for the path graph. So it's just the sum over the edges, the squared difference over that edge, divided again by the L2, mu weighted L2 norm of x. Right, and now we have that sum of mu I xi equals 0. So similarly to previously, maybe it's hard to understand what exactly this looks like when n is large, but we can try to understand what it is when n is equal to 2, for example. Right? So we have a 2-node system. So when n equals 2, we're only going to optimize over x1 and x2, both scalars, subject to this boundary condition. And you'll note that if I tell you what x1 is, this boundary condition is going to force x2 to be something else. Right? It fixes x2 for you in terms of x1. So you can rewrite that as a minimization problem over a single variable. And you'll note that that variable just cancels out as it did previously. I'm just going to tell you, I'm going to skip that stuff. I'm going to tell you that this is what lambda 2 is going to be. Okay, so it's going to be, just think of it as like the spring constant divided by the minimum mass on either side. Okay, and then, okay, so this, right, so this is what lambda 2 is when n equals 2. And again, as previously, when we have a larger graph, I'm just going to ask you to squint until all you see is 2 nodes. Right, so formally pick L and R, and we're going to consider this new graph GLR. Right, I've defined this left vertex to have the mass of the set before it, before L in the original graph, and I'm going to define the mass of this vertex to be the mass of the vertices after R in the original graph. And I'm going to connect them with a spring constant that's equal to the effective spring constant between L and R in the original graph. Right, so for this new graph, we know its exact lambda 2 value. It's going to be approximately right up to the min, the effective spring constant between the Lth vertex and the Rth vertex, and then you're going to divide by the minimum mass on either side.
Is there a physical interpretation of the boundary condition now?
Yeah, so, okay, I'm going to go back. So you could think of this as, so what does it say? You're going to sum over all the vertices, mu I xi, right? Mu is the mass and x is the position, and you want that to be 0. Right? So that's just kind of saying that the center of mass must be at 0. That's one of the interpretations. There's another part of the story though, because when you optimize this, you always get for free that the eigenvector, right, the true minimizer is going to taper off, right? So its derivative is going to go to 0. And I can explain to you what this means. It makes sense for the path graph, right? For the graph, I'm not really sure how to define it, but for the path graph at least, you automatically get these Neumann boundary conditions, if you know what that is. Okay, yeah, so I guess maybe just the interpretation should just be that, yeah, maybe the center of mass is at 0, something like that. Okay, right, so we're going to define so I'm finally going to define a Neumann content for you, right? So it's going to be a similar definition to the Dirchlet content. I'm going to just minimize this quantity over choices of L and R, okay? So psi 2, the Neumann content, is going to be defined as the minimum over L and R of the lambda 2 value, which we already know to be approximately right up to 2, the effective spring constant between the 2 vertices divided by the masses, this minimum of the masses.
Question. I have a naive question. So
Yeah.
the Dirchlet content,
Yeah.
we were minimizing over a choice of a single index, and now we're minimizing over a choice of 2?
Yep.
Why? Or just
why?
I'm not sure what kind of answer I'm expecting back.
Okay.
But
Let me think for a second.
why is the Dirichlet content over a single index and the Neumann content is over L and R?
So you can sort of think of and I'm going to make this intuition a little more formal in a second, but you can think of the Dirichlet problem, where one side is fixed, as a one-sided problem. Okay? And the Neumann problem as a two-sided problem. Yeah. Sorry, I'll show you some pictures in a couple of seconds. I think I saw Ines first.
So in one case you had a partition, right? You had a set A and the complement. In this
Yep.
case, you're allowed to pick two sets, like A and B, which are
Exactly, yeah.
some empty stuff in the middle.
Right. So notice that this is really just a definition, right? So I can do pretty much whatever I want. But in this definition, I chose to ignore all the masses in between L and R, and I chose to ignore all the spring constants within the left set and within the right set. Question?
So when you introduced the simplified graph in both this case and the Dirchlet case,
Yep.
You mentioned that you can basically show, and I assume there's some formal statement about the approximation between this value and
Okay.
that.
Sure.
But it seems like there's two separate approximations being made, because taking the minimum over the choice of these graphs
Okay.
ignores that the one of this simplified graph that best approximates the minimum of the thing you're actually trying to minimize might not be the minimum of this simplified graph. Sorry,
Okay. Sorry. Yeah. I'm not sure I completely parsed the question, but let me try to answer the first part.
Okay, yeah.
So I'm going to go back. Okay. So it's before the proof sketch. Here. All right. So when I said that that it approximates in a sense the true oscillation, right? I use like, okay. So lambda is in some sense captures like the oscillation of your original graph, of your original path graph, right? Lambda, right? Like lambda is proportional to the frequency squared of the original system, and psi is the minimum frequency squared over two node systems inside your graph, right? So I found like the best one, right? So I found the two node system inside my graph with the minimum lambda value, and that value is going to be up to a factor of 4 equal to lambda, right? So you had your original system and it was oscillating in some way, and I decided to throw away all the masses, all the spring constants after some point, and all the masses before that point. And I've shown you that the oscillation doesn't change more than a factor of 4.
So when you mentioned earlier that it's an approximation, this is what you were.
This is exactly what I was referring to. Yeah.
Maybe for models, you should just do a small example. Why don't we just take the unit weight path graph and apply this technology to it? Because
Okay.
it's supposed to give me what, 1 over n squared for lambda 2? So why
You're saying for the Neumann problem.
for the Neumann problem? Can we just on the board for us just do that?
Oh God.
Can I get a lot of people, maybe there's a lot of formulas.
Okay.
And all trivial examples.
Okay.
Cut it in thirds and just say, so the effective resistance.
Yeah, okay, sure. So, okay. So, all right, so I guess what Gary's saying is we can consider the following path graph, right? It has n vertices, right, 1 through n. And I'm going to assign the mass to be 1 everywhere and the spring constants to be 1 everywhere. Okay. Then we know that lambda 2, this is the Neumann eigenvalue, is going to be approximately 1 over n squared.
So that's what we're trying to figure out.
Or yeah, we want to show that we want to show this, right?
Well, we just try breaking it in thirds, right?
Okay, wait, but this has to do with the theorem that I haven't even stated yet, right?
Okay, either way.
Let me just skip ahead. I'll state the theorem and then I'll do the example.
I just think that a lot of people, there's a lot of formulas, and I think that there's very simple examples for which it'll be.
Sure. Okay, yeah, I'll get back to this in a second. Sorry, so we were. Okay, and right, so this is actually getting back to Ellis's point. So I'm going to think of the Neumann problem as nothing other than 2 Dirichlet problems, right, stuck end to end, right? So I'm going to pick a pinch point P, and I'm going to imagine sticking a boundary vertex at that P value, right? And then you'll notice that the left-hand side now looks like a Dirichlet problem, at least pictorially, and the right-hand side looks like a Dirichlet problem, at least pictorially. Right, so I have a Dirichlet eigenvalue, lambda g minus, this is the left part, and lambda g plus, the right part. And lambda 2 And you can show using Cron-Fisher that the true Neumann eigenvalue is nothing other than the minimum over your pinch points of the maximum of the Dirichlet eigenvalues on either side. Right, and I actually have an animation for you guys. So here we go. All right, so up at the top, that's the Neumann eigenvalue. Right, that's how your system wants to oscillate. And there's a point, right, this white point here, where like if I imagine like taking a drop of paint and like putting it down on that edge, that drop of paint is not going to move. Right? So I can imagine like wanting to like hold that point at 0. Well, if it wanted to like stay there originally, then I really haven't changed the system at all. Right? So the left half, right, is just this graph here. Right half is this graph, and it's still going to, both of these are going to oscillate at the same speed as the original one. Right? Because like really I didn't really change the system. I could imagine like moving this white point, this boundary point, to the left, for example. Okay, so as I move it to the left, right? So for example, this is the left half of the graph now has 2 points. Right, that's these 2 points here. This side is going to begin to oscillate much faster than the true Neumann eigenvalue. Okay, and this, and the right half is going to oscillate slower. Right, and wherever you go, one of them, so as you go to the left of the true value, this red line here, the left side's going to oscillate faster, and on the other side, the right half's going to oscillate faster. Right? And they're only equal right where the Neumann eigenvalue wanted to be at 0. Okay, so let's return. Right, so using this lemma, it's easy to prove this statement, which is, maybe I'll skip the proof. And do Gary's example instead. But here's the theorem statement: is that if I choose the optimal, if I choose the two optimal L and R, then the Neumann eigenvalue of that system is up to a factor of 4 lambda 2, equal to the original lambda 2. All right. Okay. So, all right. So the Neumann. Let's try to figure out what the Neumann content of this graph is. Right, so by definition, this is going to be minimum over L less than R of, right. Okay, so in the numerator, we had the effective spring constant, right? And so that's just going to be 1 over the length between them, right? Right, so it's going to be 1 over R minus L. And the minimum of either side, I'm just going to pretend this were the minimum, okay? So here I'm going to have the minimum of L and I guess N minus R plus 1 or something. So if you pick any L and R, you might as well make these equal, right? Because otherwise you could just increase, or you could decrease, or you could increase the inside term and decrease the whole term. Right, so I'm just going to imagine that L is this value here, and R is also L distance away from the other side. Right, so this is going to be minimum over L less than n over 2 of 1 over, this is going to be n minus twice L times L. And I claim the minimizer is going to be approximately like n over some, it's like some constant times n, right? So you're going to get a quadratic term, right? So it's going to look like 1 over n squared. Okay?
Intuitively, you're just going to break it up into thirds and have one side be the mass be the 2 outer thirds,
right.
And the middle third just your effective resistance.
Yeah, up to constants. Yeah, so you're going to pick a constant size portion over here, a constant size portion over here, and then you'll get a constant size resistance term. Or 1 over, you'll get a constant size 1 over spring constant term. Okay. All right, so I'm going to skip this because we're running out of time. But I'm just going to tell you how this theorem generalizes. Right, so we've seen it for path graphs today, up to that part that I didn't present. You can also do it on a general graph, right? So if you have a set S a subset of the vertices, you could think of the previous problem as being the Dirchlet problem where I'm going to fix V0 to 0. Right? You can also define a similar quantity where you're fixing all of some set to 0. And I'm going to denote that by lambda gs. And you can define a suitable generalization of psi as psi gs. And you'll get psi over 4 is less than lambda is less than psi. Right? So similar theorems. And you can do the same thing with the Neumann, with a regular graph. Or sorry, not a regular graph, but like an arbitrary graph. And you'll get that, you can estimate it the same way. Another generalization is if you care about the P Laplacian, is that you can do the same thing for the P Laplacian. You can define lambda 2 for the P Laplacian. You can define a generalization of the Neumann content for the P Laplacian. And you'll get that lambda 2 is bounded above by psi 2, is bounded below by psi 2 over P q to the P over q.
What's the P Laplacian? Sorry,
Yeah, sure. I actually didn't define the P Laplacian because I'm not sure too many people in this room care about the P Laplacian.
Maybe
but,
I can unask the question and we can talk more.
Okay, yeah, I can talk to you. We can talk offline. The normal Laplacian is a 2 Laplacian. Right, so you can check that when P, right, so Q is a Holder dual of P. So when P equals 2, the denominator is just 4, right? So it's the exact same theorem, and this is also tight, right? This is also tight for, this is the optimal constant you can have here.
So did Muckenhout have a P version of his?
He did, and that's exactly how you get this. All right, sorry.
What was the Q in that equation?
Oh, yeah, sorry, Q is a Holder dual of P. So like 1 over P plus 1 over Q equals 1. Right, so P defines Q. Okay, all right, so I'm just going to summarize. So we saw this cute inequality called Muckenhout's weighted Hardy inequality, and we realized that it was nothing other than a statement about Dirichlet eigenvalues. We defined for U the Neumann content, which looks like this thing here, and we thought we can think of it as a generalization or a relaxation of the sparsest cut. And with this definition, we showed that you could estimate lambda 2 up to a factor of 4. All right, and so I think the main message of this paper or of this work is that it'd be cool to see if there are like approximation algorithms that you could develop out of this inequality here. Right, so there are a lot of approximation algorithms that use Cheeger's inequality. Right, so the draw of using this inequality as opposed to Cheeger's inequality is that this would work in a much wider range of settings. Right? We don't require that the masses be equal to the degrees. And we also get a much tighter estimate. Right? So it'd be cool to know if there are ways to apply this to approximation algorithms. And that's it. I'm taking questions now, I guess. Yep.
So the goal is just to prove that theorem, but what if you wanted to compute lambda 2? What's the algorithm for doing that?
Oh, so usually you would start with like some random random vector, and then you would just invert the matrix, right? You would just do like an inverted power method, inverse power method. Yeah, so that's usually how people find that.
It's not that hard to compute it, so why is this useful?
It's right. So this goes back to the previous point. It's that sometimes lambda 2 is really hard to nail down analytically. Right? You can compute it numerically on your computer, but if you actually want to like sit down with pen and paper and try to figure out what lambda 2 is, that could be a really difficult task.
So when Alan Friese wanted to do his volume calculation by doing random walks, he needed to know that something about lambda 2. How did he do that? He said, well, the graph has no small cut.
The rapid mixing.
So get the mixing. So that's how it works. So what you want to prove, you got a linear system solver, and you want to know that it's fast, you need to estimate lambda 2. And the simplest way usually in the past has been that linear cut using Cheeger. But then you're off by something quite large. But like in this example here, you should point out that this estimates lambda 2 between 1 over n and 1 over n squared by a huge amount.
Mm-hmm.
Right? And so this gives a much tighter estimate. That was right.
This gives a tighter estimate.
Yeah, I think understanding these simple examples is, but yeah. You
So
should show it.
if you plug it into Cheeger, it would give you some very loose bound.
Between 1 over n and 1 over n squared.
Okay.
So Alex,
Yes.
like for some kind of Markov chain system, maybe sort of on matching, so maybe something even simpler.
Okay.
Can we actually use this to get a better estimate of what the...
I know that this has been used.
Okay.
So we weren't the first people to realize that you could use this to bound some eigenvalue. To my knowledge, I haven't seen anything doing this with graphs or the Neumann eigenvalue. Like what I have seen is the Dirichlet eigenvalue on an infinite path graph. And I have seen that used for Markov chains in that setting. Yeah. I have not used it myself. Yeah. Yep.
So, this gives a factor 4 approximation for psi2. Does it also give a solution for the search problem if you want to find the A and B which minimize this?
So we've thought about this a little bit, and I don't have any answers for you. On a path graph, it's right. You could just sweep cut. On an arbitrary graph, I don't know how you would try to find A and B. Yep.
Yeah, I just want to find out that so in expanded vexing lemma,
Mm-hmm.
you're minimizing the number of edges crossing A and B.
Yep.
Divided by square root AB instead of
okay.
minimum of A
Sure.
and B.
Okay.
And yeah, maybe this gives a version of like a closely related inequality to expanded vexing lemma that's more generalizable.
Okay.
That's more useful.
I see.
The only version I know is on regular graphs.
Okay. Maybe we should talk about this after.
So one more question sort of triggered by Anupam's point. So,
Sure.
so usually the regular Cheeger, you say lambda 2 is at least conductance square, and then
Sure.
you lower bound conductance. This is the other thing where you're trying to prove some chain is mixing. Then
Sure.
you lower bound conductance using canonical paths or all these
Right.
tricks.
Yep.
So do those quantities also lower bound psi2?
Uh,
Or do you have some proxies like canonical paths and so lower bound psi2?
We don't yet, and they don't. And I think that's a good question. So it's not clear to me, but it's something that I should think about. Yeah.
The first
Yep.
time Gary mentioned this stuff to me, he kept talking about Hardy.
Yes.
And now this new guy came along.
Yes. Okay.
Because you discovered that Hardy's inequalities have been generalized in the meantime, in the
Yes.
last 100 years, right?
Right.
The version that you used
Yes.
today.
Yep. So the original Hardy inequality. Okay. Oops. So let's go back to. Okay. So the original Hardy inequality had to deal with when mu and kappa were fixed, right? Hardy's inequality says, right? You can forget about all the stuff down here. Hardy's inequality says that if mu sub I is equal to 1 over I squared, right? So the masses are decreasing quadratic, like 1 over n squared, and the kappas are constant, right? Then the optimal constant here to put here is 4, and that's Hardy's inequality.
Okay.
Yeah, Hardy's inequality really. Okay, so I said that you would take mu I to be 1 over I squared. How you think about that is you're going to take mu sub I and you're going to stick it into this quantity here, right? And this quantity is going to become the average. Right? It's the running average as opposed to the running sum. And Hardy's inequality gives you an upper bound on the, the operator norm of the average operator. The running average operator. Yeah. All right. I guess I'll take any other questions offline if there are any.